This is the video solution of questions from 31 to 40. The first question that is a doubt is question 31. Okay. It says the value of delta GF of mercury, of gaseous mercury. Let's first start with the equation. Uh, Formation enthalpy of gaseous mercury can be written as the equation in which liquid mercury, standard state, is converted to Hg gas. The delta GF naught for this process is given. It's 31 into 10 to the power 3 joules per mole. What total external pressure mercury starts boiling? Okay. For this we can write that delta G naught is minus RT ln Kp, where Kp is partial pressure of mercury vapors. In this case, in this question, delta G naught is given to you, temperature is required, and P naught, which is the external pressure, that is asked actually. Okay, the temperature is 25 degrees Celsius. So this temperature is given as 298 Kelvin. This is what is asked. I think everything is known in this question, right? Temperature is known, R is known, delta G naught is known. R, of course, you use R naught, R value is 8.314 in this case because delta G is given in joules. Right, so the next question is question number 32. Question 32. What is delta G reaction for the synthesis of ammonia and the following set of partial pressures? Delta G naught is given to us, right? So we use this equation. We use the equation delta G is delta G naught plus RT ln Q, where Q for this question is partial pressure of NH3 squared divided by partial pressure of 2 into partial pressure of H2 cubed. Of course, you have to remember that when you use Q, this expression, you have to write pressure in bar. In this equation, we cannot use Q. We cannot use an expression for Q which gives you any residual unit. So you have to actually take the activities of the gases involved in this case for the value of Q, and the activities are equal to partial pressure in bar. So in this case, partial pressure in bar has to be used. Right, the next question is question 34. Calculate log of C by A. Now see, you start with 2 mole each of A and B. Number of moles of A and B are same at the beginning, and they are consumed in a 1:1 ratio. So even at equilibrium, concentrations of A and B will be same. And that goes for C and D as well. C and D will be equal to each other because they are being formed in a 1:1 ratio. Now for this reaction, we can write delta G naught as minus of RT ln K, where K is C concentration into D concentration divided by A into B concentrations, which in turn becomes concentration of C squared divided by concentration of A squared. That is what is asked. These are equilibrium values. So using this equation, you can calculate the value of C by A concentrations. Question 35 next. 1 mole of an ideal gas, change in entropy. So we leave 10 times of its initial volume. I think it's at 25 degrees Celsius. It does not say anything about the temperature, so I think it's an isothermal process for which the change in entropy delta S simply becomes nR ln of V2 by V1, with the final volume being 10 times the initial volume. Okay, next. Right, for question 37, it says A to B is a reversible isothermal expansion, followed by B to C, which is isochoric cooling, and C to D is a single stage adiabatic compression. It is easier to solve these questions if you have a graph. So let's first draw this, denote this on a PV graph. Right. So the first process is a reversible isothermal expansion. This is A with pressure values and temperature values are given. This is 500 Kelvin and 5 bar. B is an isothermal process, so the temperature has to be 500 Kelvin again. B to C is isochoric cooling, and the temperature becomes 250 Kelvin and the pressure is 1 bar. Okay, so because B to C is isochoric, V is constant, so P by T has to be constant. So if the pressure here is 1 bar and temperature is 250 Kelvin, then for state B, the pressure has to be 2 bar. P by T has to be constant in both cases. Now from C to B, you have a single stage adiabatic compression. So it's a single stage adiabatic compression which we have here. And at D, the final pressure is 3 bar. The temperature here is not known. Now the first option is for the pressure at B, which is 2 bar. We've already found this out by using that BC is an isochoric process. Then for the temperature as D is required. For evaluating the temperature at D, let's use the process CD. For the process CD, which is irreversible adiabatic compression, we generally use this. We write two different formula for work. One of the formula is minus of P external into delta V, but this can also be written as NCV delta T. Because this is an adiabatic process, Q is 0, so W and delta U are same. So delta U is equal to W. Now, in this case, P external is same as P2. Because it's a single stage adiabatic compression, the external pressure and the final pressure are same, 3 bar. Delta V, let's write it as V2 minus V1. This is N, CV is known, and this part is T2 minus T1. Now, in this case, N, CV, and T1 are known. T2 is the only variable which you have here. For the left hand side, P2 is known. I write V2 as N R T2 by P2 and V1 as NR T1 by P1. So in this case, NR T2, I think T2 is the only variable in this set of equations. So you can use this and solve for T2. Now once you've solved for T2, delta H for this process can be written as NCP into delta T. Once you've solved for temperature at D, delta T will be known and this can be evaluated. The same thing goes for delta U as well. Okay. Now the next doubt is question number 38. In question 38, you need to write evaluate slope of curves. For that, you just need to write the equations, right? PV to the power gamma is equal to constant, for example, for C, and differentiate it so that you get a value of dP by dV. The value of dP by dV will give you the slope in this case. Okay, the next question is question 39. In question 39, options A and D can be solved just directly from the graph. The option A is work done the gas from A to B. If it takes place in a single step, isothermal expansion. If it had been an isothermal process, you would have a graph, let's say like this. So for the isothermal process, obviously work done can be evaluated as area under the graph, and it is less compared to the straight line path from A to B. So work done by the gas is higher in the straight line process from A to B. And the option D says that in going from A to B, the temperature of the gas first increases to maximum and then decreases, right? Now see, along the blue line that we have here, temperature is constant throughout, as it's an isothermal graph or isothermal plot. Now the temperature here at A is same as temperature at B. That I forgot to mention. We know that because, as you can see, at A the product of PV is P into V, and at B the product of PV is again same. So A and B have identical temperatures because PV product, which is nRT, is same for both cases. Right, so that's how we know that this is an isothermal process, and the isothermal pass through A and B. Now, because this yellow line, or rather the blue line, gives you constant values of temperature, greater the difference that you find here, greater will be the temperature on this particular path. As you can see, the difference keeps on increasing and reaches a maxima. So maybe around here the temperatures become highest, and then the temperature again decreases, or the difference again decreases, so that it returns to the original temperature B. That's it.